This first video in chapter 6. It's an exciting chapter where we are going to actually start learning about organic reactions, and really chemistry is about transformation of molecules, right? So we're changing of molecules, really. So like this is really where organic chemistry really starts, you could say. And the first reaction we're going to think about is are called SN2 reactions, and then I think I hope I have time for this, but during class time we'll probably talk about sort of real life examples of SN2 that really would have direct application impact on your life, as well as sort of medical implications and whatnot. So with that said, let's think about this type of reaction. So SN2 reaction, it stands for nucleophilic substitution bimolecular. That's what the 2 means, is the bimolecular part, and S, of course, it's substitution. N means nucleophilic, and so the nucleophile is going to substitute for something, it replaces something, and that something is called the leaving group. But I guess I'm a little bit getting ahead of ourselves. First, we need to kind of talk about what does it mean to be nucleophilic, or what is a nucleophile, which I hope you still remember this from Chem, right? Nucleophile is something that as the name suggests, phile, right? Like this means loving, and then nucleo means, well, nucleus of an atom. And if you think about what is in the nucleus in an atom, that's where all the positive charges are, the protons, and then it's on the outside that you have the electrons. And so for that reason, nucleophiles, you could say, is something that is positive charge loving. Things. Okay, so that means nucleophiles themselves are usually negatively charged, or at least electron rich. So nucleophiles might come in this generic form with a negative charge, but at least even if it's not negatively charged, the nucleophile has to have a lone pair, must have a lone pair. Technically, there could be an exception to that. It could be having a pi electrons. Then you could that could be a new form of a nucleophile, but it needs to be electron rich. So you need to have a lone pair or some pi electrons, and electron rich, and it needs to be polarizable. Electrons kind of could spread out, or it could accommodate charges. This usually means the bigger the atomic size, the better nucleophile, and also resonance helps. Because that makes it more polarizable, like it can accommodate charges. And bulky things like big molecules, they tend to not be nucleophilic, because that bulkiness kind of gets in the way of acting as a nucleophile, as we'll see. So what is a nucleophilic substitution reaction? What would that at least generically look like? Let's say we have this sort of generic nucleophile with a negative charge. What this does is it will attack, and then we usually use the word attack to mean that the nucleophile bonds with some sort of a carbon compound. That's depicted by this generic R, which, by the way, R technically stands for the rest of the molecule. Typically this happens because this, what we are calling the leaving group, is at least electron withdrawing, so often partially negatively charged. Remember, this delta sign means partial charge, which makes the R group sort of electrophilic. So we could say that this LG, this stands for leaving group. it's called a leaving group because, well, it leaves. And the R, this is the electrophilic substrate. It shouldn't be surprising to you that the nucleophile wants to react with an electrophile. Right, electrophiles are typically positively or partially positively charged. It wants something that's electron rich. That's why it's electrophile. And so now the nucleophile is attached to that R carbon, and then now the leaving group gets those 2 electrons right here from the bond. That's where the lone pair, extra lone pair comes from, and that's a typical nucleophilic substitution reaction. And a slightly different variation of this that you might see in this chapter is when the nucleophile is still nucleophilic with a lone pair, but it's not, it doesn't have a charge. In that situation, you might see something like this. Right, same idea. This lone pair of electrons attack the carbon. So this arrow is signifying how you're going to have, this R to Nu bond, and then this bond breaks, and once it breaks, you would have the leaving group negatively charged. But if the nucleophile didn't have a charge to begin with, it's going to negative charge to begin with. You're going to have this. So, right, between the two, can you guess which reaction usually happens more readily? And that's the top, because you're going from one charge to one charge, from starting material to the product. In the second case, you're going from neutral to charged species, which is not as energetically favorable. Now, of the nucleophilic substitution reactions, SN2, the mechanism we wrote here is really technically an SN2 reaction, but let's kind of delve deeper into that a bit, the SN2 reaction. And as we said, that stands for nucleophilic substitution bimolecular reaction. And here's an example of that. On the left, we have the electrophilic substrate, and this is electrophilic because the bromine is electron withdrawing. It's partially negative, which makes the carbon that it's attached to partially positive, and so for that reason this is electrophilic. At least that carbon is. By the way, can you name this substrate as a means of review? If you pause the video, this is R2-bromobutane. Okay. Hopefully you remember how to assign R and S and whatnot. And then it's reacting apparently with sodium hydroxide. You probably learned this in Chem as well, but remember, sodium is almost always just a spectator ion. It's being good at like not doing anything, right? And so that means that the this hydroxide ion is the nucleophile. Okay, so that's the hydroxide ion. And then there's some sort of a solvent, and the product that we're going to get through SN2 reaction will look like this. And I don't really need to really show this. This is not important byproduct. But sodium and bromide could form a salt. That's sort of the byproduct. And we're going to talk about the mechanism, essentially what's happening with the electrons. Now, it's not like we can, if you use a microscope, you can look at what the electrons are doing. You can't see like these tiny molecules necessarily with a microscope. So what are some evidence, actual experimental evidence for what we say and what we do in the mechanism, right? So what are the actual observable things? If you do this type of SN2 reaction, or if you do SN2 reaction, one of the first things you notice is if you look at the kinetics or the reaction rates, hopefully you still remember the rate law equation, is some constant times the starting material or starting material concentration. And the reaction rate, if it's an SN2 reaction, depends both on the nucleophile and the haloalkane, or you could say the electrophilic substrate. The point of this is it depends on two things, meaning this is the second overall reaction order reaction. Okay, it's a second order reaction, meaning it depends on both of these concentrations, not just one. First order would just depend on one thing. And the second observation might be that there is a stereochemical inversion after the reaction happens. Okay, so the mechanism we come up with need to be able to explain both of these phenomena, and that's what you do in a mechanism. We come up, it's really just a sort of imagined thing that might be that could happen with all these atoms that are, but it's not just purely imaginary, because they're backed up by the actual experimental observations and other related reactions that we know about. So it's a very legitimate thing that's reliable, but that's how the mechanism is usually derived. So just to go over this again, it has to involve both the nucleophile and the substrate. In RDS stands, hopefully you remember this from Gen Chem, stands for rate determining step. It's RDS. And the mode of attacking, or the collision of the two molecules, must be through the backside attack, and then we'll talk about what that means in a second. But let's say, I hope it makes sense to you, but this is the same molecule as that. Here's methyl and ethyl group and a bromine. And the nucleophile, in this case, is the hydroxide. It's a nuke. Right? And what we mean by the backside attack is here's the nucleophile coming in and attacking at this carbon, and here's the leaving group leaving in one step. That must be the mechanism through the backside attack. And what we mean by backside attack is that the nucleophile is coming in from the exact 180 degrees opposite of the leaving group. Okay, so that's what backside attack means. And then if we look at the sort of transition state, during the transition state, the molecule basically should look like this. Oops. Here's the carbon being attacked. Here's the ethyl group. Here's the hydrogen. And the hydroxide is beginning to form a bond with this carbon, and the bromide is beginning to leave and break that carbon-bromine bond during the transition state. That's what that must be what's going on that leads to the inversion of stereochemistry. Okay, and so what we're saying is like this whole carbon here that's being attacked momentarily just during the transition state becomes sp2, which is flat, right? whereas in the study material, of course, the hybridization is sp3, and through that transition state you get a product that's also, of course, sp3. By the way, SN2 reaction can only happen on an sp3 carbon, because if it's an sp2 carbon, there's no way that the nucleophile can be lined up 180 degrees opposite of the leaving group. If you think about it, maybe with a molecular model kit, that should be pretty apparent to you. And if we look at the stereochemical assignment, we started out with R, and notice it ends with an S assignment for this alcohol. So there is an inversion. Right, so this mechanism, I hope it makes sense to you. It's really just one step. There's only one step in this mechanism, which means that is the rate determining step, because there's no other step. And in the rate determining step, we're showing the involvement of both the nucleophile and the substrate. So that is consistent with this rate observation, second order overall. And through this backside mechanism, we should see an inversion. So we can explain both of these observations. So this must be the correct mechanism. Now, just so you understand what the backside attack really means, let me just kind of show you what we would mean if this was a front side attack. Okay, and that would look kind of like this. Right, the front side of the leaving group. And so if that really happened, we should have a retention of stereochemistry, which of course we don't observe. Like, this is not true, right? So that doesn't happen. Now, maybe you could pause the video for a second and see if you could do this practice problem. What would be the product structure here? Okay, and that should be, hope you paused it. Cyanide is the nucleophile. Sodium, of course, is a spectator ion, so you shouldn't think about that. Okay. All right, well, I'm sure do more practice problems in class, and I'll see you then.